So the topic I want to discuss is today what is called pitot tube, something related to pitot tube. This is in fluid dynamics. See, I told you there are three things. One is called Venturi meter. We'll talk about this. I discussed about Venturi meter previously. Then we have what is called this pitot tube, which is based on certain principle which we'll try to understand today. A slight modification of this is pitot Brand tube, which is a slight modification of this. So Venturi meter, I told you that you have got a pipe whose cross section is narrowing in this manner. Okay, so you have got certain area of cross section here, which is A1, and suddenly it narrows into a smaller area of cross section, which is A2 here, and again which will come back to the original area of cross section A1 here. So water is flowing here. Okay, if I apply Bernoulli, if I take the pressure here is P1 plus if I take here the speed as V1, so half rho V1 square, and suddenly when it comes to this constriction, this narrow portion, we saw that when water enters the narrow portion where area is less, their speed is more. So here the speed is more V2, where V2 is or I'll write V2 more than V1. And if I equate the pressure, the static and dynamic here, so we have got this P1 plus half rho V1 square. Okay, that is the two terms of Bernoulli here. Third term I am not writing because I am considering the tube to be horizontal. So rho GH term at both points will cancel off. Is P2 plus half rho V2 square. Now if V2 is more than V1, this term will be more compared to this term. So pressure has to be less compared to P1. Okay, so pressure here which you are recording will be less. Now take a note, what is the pressure you record here if you use a manometer? What is a manometer? A U-tube kind of structure. The pressure you record here is P1, which is what we call as the static pressure. Okay, so the pressure you are recording there is P1, which is the static pressure. This half rho V square term is called dynamic pressure. Dynamic pressure. So if I show this construction on the next page, in a better way. So this is the Venturi meter. Okay, so area of cross section here I have taken it as A1. Area of cross section here is A2. A1 is more than A2. So by continuity, V1 is less than V2 if I call the speed here as V1, and if I call the speed here as V2. V1 is less than V2. Then if I use Bernoulli, the pressure here if I call it as P1, P1 plus half rho V1 square is P2 plus half rho V2 square. Because V1 is less than V2, this term is less compared to this term. So pressure at P1 has to be more compared to pressure at P2. And how do you measure these pressures? If I show an extra construction for you, maybe you can have here a manometer. What is a manometer? A U-tube basically. So I have got a tube which is something like this. Let me try to draw it better. So it looks like this. Okay, you can have some other liquid here, maybe mercury. Now because here P1 is more, the pressure, so it's going to press this mercury more. So this mercury will be down and this level of mercury will be up. So this is all mercury. So this is called manometer. Okay, a simple U-shaped tube in which you have certain other liquid. Now the pressure that you are measuring on this side, it is nothing but P1. This is what we call as the static pressure. Static pressure. Okay, because in Bernoulli there are three terms: P1 plus rho GH plus half rho V1 square. Here we are not writing that rho GH term because it is a horizontal tube. So at point 1 and point 2, at both area of cross sections, the rho GH term will be same, so that is getting cancelled. So the pressure we are measuring here is P1, okay, and the pressure here we are measuring is P2. Because P1 is more, it compressed the mercury a bit more, and this is as I have shown here. Okay, in fact pressure here at the same level as that side will be same. This will be P2 plus rho G, this height, if I call it L, that will be P1. So P1 will be P2 plus rho G L. So P1 is more than P2. So the pressures you are measuring using manometer when a liquid is flowing in a venturi meter is the static pressure. Okay, the static term P, that is what you are measuring. Of course, the value of the static pressure depends on the dynamic pressure, which is half rho V square. Because if half rho V square term is more, then to keep the sum constant, P1 has to be less. Similarly, if half rho V1 square is less, P1 has to be more. This is our idea. Okay, now generally venturi meter is used to measure speed of fluid in a pipe. Generally venturi meter is used to measure speed of fluid in a pipe. For example, suppose there is a pipe which is carrying certain fluid and you want to measure the speed of the fluid in the pipe. What you do, you remove certain section of the pipe, maybe it is fixed with screws, so you remove that section. So you remove this section of the pipe, you temporarily disconnect it, and here you connect a venturi meter. So in that section where you remove the portion of the pipe, you connect a venturi meter like that. Okay, and to which there is already a manometer connection. Okay, U-tube kind of connection is there, a manometric connection is there, from where you can try to measure the pressures at the thin section and the fat section of the venturi meter. So basically, by knowing the height difference, okay, you can measure the pressure relation here, and by using Bernoulli you can measure the speed of water. So this is one of the purposes of venturi meter. So venturi meter generally used in fluid dynamics laboratory to measure speeds. Or of course there is nothing wrong, if a river is flowing, you can put this venturi meter in a river, but this cross section has to be quite big, and so that, because at the edges the river flow is altered, so we are allowing the river to enter into the same speed as it was flowing in the venturi meter, then it is narrowed, okay, so that the speed will be more, then again it becomes fat, this venturi meter, so speed comes back to normal, and again there will be a manometric construction from which you can measure the speed of the river if required. But there is another device which is called a pitot tube, which generally we use to measure speeds of let us say a river. When you have a boat which is going in a river, you want to measure the speed of the river, you use this pitot tube. It has got a slightly different philosophy than venturi meter, we will look into that philosophy. Or this pitot tube can be fixed to an aeroplane, an aircraft, at different angles, and try to measure the speed, how it is coming in the direction of aircraft or opposite direction of aircraft or perpendicular to aircraft. You can arrange this pitot tube in different directions and try to measure the fluid speed across different cross sections, across different directions. So what exactly is a pitot tube? We'll see that in a minute, but before that we have to understand something called stagnation pressure. pressure and stagnation points. Stagnation point. This is very important. Suppose I have a fluid which is flowing, let us say in a river, let us say for example, and the flow is, let us say, ideal, which means the fluid is incompressible, the liquid is incompressible, irrotational, and you have got no friction between the layers of fluid and so on, all those ideal assumptions. So the fluid is flowing, okay, in a laminar way, laminar flow. Now suppose in this river you put a cylindrical object, okay, at the center of the river. So the cylindrical object is placed vertically, that means its length is dipped into the river. So you see a cylindrical cross section like this. This is the cross section of cylinder. So if the screen is the river, you are putting it into the river like a shivaling which is put inside a river, you know, like Bahubali and so on. So you have a cylindrical object. Now what happens, you know, very interesting thing happens here. I am going to show it with a blue line. The river which is flowing, because now it is encountering an obstacle, some part of river will take a turn here and will go through the upper section of the cylinder and go like that, in that manner, and some part of the fluid will go in the lower section. Let me draw it properly, like that. It will go in the lower section. So you see the fluid which is coming, some part is turning upside, some part is turning downside, okay. So the velocity is changing. If here it is as a vertical component, as you come down the vertical component is less, somewhere the vertical component becomes 0 and there is a vertically downward component. I am saying here vertically downward and up, but in the river it is leftward and rightward component. This is the left component of velocity. It has a left component because it is turning and going around the obstacle. Here it has a right component of velocity. So there exists a point, a particular streamline, where there is neither leftward component nor rightward component, so where velocity of the fluid is 0. So here velocity of fluid is 0, because this fluid flow, the velocity flow, the flow velocity is continuous. Continuous means there cannot be any break in the flow velocity. So it is gradually changing from leftward to 0 to rightward. So there exists a point where fluid velocity is 0. This point where fluid velocity is 0, very near to the obstacle, this is called a stagnation point. This is called a stagnation point where fluid velocity is 0. Okay. In fact, from here onwards, whatever fluid is there between this point and the cylinder, that fluid has no velocity. It is kind of attached to the cylinder, let us say. The fluid there is attached to cylinder. It is just at rest there. Okay. That is the thing. And on the other hand, here the fluid velocity is maximum. Okay. At the edge, at the sides of the cylinder, at the sides of the cylinder. So the fluid which is directly coming towards the cylinder, it will stop. There is a stagnation point, and at the sides the fluid flow is more, the fluid velocity is more. Okay. It is because what is happening here, the streamlines are trying to come closer. So when streamlines come closer, the fluid speed will increase. So at the sides here, streamlines are coming closer. It is like going through a constriction, going through a narrow passage. So here speed of the fluid is more. In fact, some experiments show that the speed at the sides is twice the actual fluid flow of the river. It so happens. Okay. So at the sides, that means here the fluid flow is 2 times having a speed which is twice the normal fluid velocity. Okay, some experiments reveal that. Anyway, our concern is with the stagnation point. Now let us look at the pressure at stagnation point. So this is my cylinder. Suppose the fluid here was coming with a velocity v1, pressure there was p1, and when it comes to stagnation point, their speed is 0, and let us say pressure there is p2. Okay, and this is all at same horizontal level. So if I apply Bernoulli, p1 plus half rho v1 square is p2 plus half rho v2 square is 0, because at stagnation point there is no fluid velocity. So the pressure p2 which you are measuring with a manometer, because with manometers what do you measure? You measure the static pressure. The pressure p2, which is the static pressure here, is actually sum of static pressure and dynamic pressure where there was no obstacle. Okay, so the pressure p2 what you are measuring is actually sum of p1 plus half rho v1 square. This p2 is called stagnation pressure. Stagnation pressure, its value happens to be equal to the normal static pressure in a fluid plus the dynamic pressure. Together you are able to measure now as a static. So at point 1, if you use a manometer, you try to measure only p1. You measure the static pressure. You don't know what is the dynamic pressure, half rho v1 square. But when you come to point p2, which is the stagnation point, there the pressure which you are measuring in value actually happens to be p1 plus half rho v1 square. Together this you are measuring as the static pressure. So if you take the difference between the pressure you measure here with manometer and what you measure here with manometer, that p2 minus p1, the two pressures, the differential pressure comes out to be half rho v1 square, which is the dynamic pressure. So suppose if I have a manometer which is looking like this, okay, certain kind of U-tube, okay, with certain other liquid. My diagram is not very perfect. Let's like this. Suppose you have a manometer, okay. So the differential pressure which it is measuring due to the difference in heights of mercury. So here suppose you have some liquid which is going to certain height. Here you have a liquid going to greater height. Why greater height? Because this pressure is more. So the difference in heights which you are measuring, that gives you difference in pressure p2 minus p1, which by Bernoulli comes out to be the dynamic pressure. So you are able to measure the dynamic pressure using a manometer, okay, and from there if you know the density of fluid you can get the speed of the fluid. So this philosophy we use it in pitot tube. Okay, here we had a cylindrical obstruction, a cylindrical object which we placed as obstruction. Okay, but pitot tube does it in a very beautiful way. So our pitot tube, actually how does it look? Simple. The pitot tube looks like this, let us say. So this is all the material of the tube, and this is the hole which is passing through the tube. This is the hole, okay, and it's a dead end, okay, and it is closed here. It's a dead end. It's a dead end, and you may have some construction here to measure the static pressure. Maybe it could be connected to a tube, okay, which can be connected to mercury, which is connected to some other gas or something here. So to measure pressure, to measure the pressure, okay, or it can be connected to a pressure gauge to measure directly the pressure. But basically what is a pitot tube? It is just a flat tube. It is just a tube with a narrow hole like this, which is going to a dead end, okay. And of course if you want to measure pressure of the air or the fluid which is there inside this thin hole, there will be some other extra construction which you can use to measure it. Now what is happening, when you put this pitot tube in a river or you attach it to a aircraft and so on, what happens is the air which is coming or the water which is coming around the tube, it will try to flow like this, and around the tube it will try to flow like this. So you see the water is just going around the tube. So obviously there will be a stagnation point here, okay, because this is also some kind of obstruction. So inside there may be air or there may be stationary fluid which is not moving. It doesn't matter, that's not my concern at all. But here there is a stagnation point, that means the fluid velocity here is 0. Okay, from here onwards, if there is fluid, it has 0 velocity. That fluid could be air or that fluid could be some other liquid. I really am not concerned with that. So what is happening here, if the pressure is P1 and if the speed of the fluid is V1, by the time it comes here, the pressure is P2 and the speed of the fluid is 0. So plus half rho V2 square term is 0. Here there will be P1 plus half rho V1 square. Okay. So the point is, if somehow you can measure the pressure at stagnation point, which is same as pressure everywhere inside, so you can have some other construction here to measure that pressure. Maybe a pressure gauge is there to measure that pressure. The pressure that you are measuring here, P2, which is a static pressure only, but actually it is sum of two terms, P1 plus half rho V1 square. That is nothing but it is sum of static and dynamic pressures at some other point where there is no obstruction. So the pressure P2 which you are measuring is more than P1. In fact, it is P1 plus half rho V1 square together, which you are measuring now as a static value, as a static pressure using pitot tube. Okay, we call it in fact stagnation pressure. This pressure P2, the pressure at point P2 is called stagnation pressure. Okay, the stagnation pressure is P2 is what is it? P1 plus half rho V1 square. It is static pressure at some other point where there was no obstruction, plus also the dynamic pressure. So stagnation pressure is static plus dynamic pressure at some other point where there was no obstruction. Okay, so stagnation pressure which you are measuring contains both the static and dynamic values of a moving fluid. Okay, so this is a pitot tube. Now there is a extra construction to a pitot tube to make it what is called a pitot Prand tube. So what you do there, you have the same pitot tube only, no difference, but it can have a small narrow hole there, and this will also have a small narrow hole here, or series of holes can be there. So now what is happening, you look at this construction carefully. There is a small hole here, and there is also a small hole here. Okay, this inside could be air, whatever is the shaded portion could be air, or it could be some other fluid, I don't mind. So you are trying to, and what happens is, you will have a manometer now, which I will show with red color to make more impact, which is connecting to the inner tube like that. Okay, and also which is connecting to this outside tube like this. So you have got a manometer here, let us say. Okay, and it looks like this. There may be mercury here. This red colored liquid, this is, let us say, mercury. Now this construction is called pitot Prand tube. So what is happening here, when you put this inside a moving fluid in a river, let us say, so the river water is coming, so here the river water will go upside around the tube and go downside around the tube, and here is the stagnation point. Okay, the pressure here at the stagnation point and everywhere inside, okay, including in this, in this red colored tube is, so the pressure at this point ultimately is coming out to be stagnation pressure, which is P1 plus half rho V1 square. That is the pressure here that you are measuring. Okay, you are measuring this as a static pressure. Actually this is P2, so you are measuring P2, which is actually sum of two terms. You are actually measuring here P2, that is the static pressure only, but its value is actually P1 plus half rho V1 square, the value. Okay, don't think that you are measuring dynamic pressure here. You are measuring it as static value only, but its value happens to be sum of two terms, P1 plus half rho V1 square. Whereas the fluid which is moving here more or less is going with the constant speed as the remaining of the river. So the pressure in this section, which I will show with a purple color, the pressure in this section, if there is air or any other liquid, whatever, if there is air, it is same as normally what you measure in a river, which is P1. So the pressure here at this point is P1 that you are measuring. So what is this difference in height actually that you are able to measure here? The difference in height, it is the pressure is P2 minus P1, and P2 minus P1 happens to be half rho V1 square. So if you measure this height, so this rho mercury into G into H is half density of water into V1 square. From here you can get V1. Okay, so speed of the river can be calculated using this arrangement, which is called a Pitot-Prandtl tube. Okay, so what you are measuring using this? You are measuring the differential pressure P2 minus P1. That is, you are measuring the dynamic pressure indirectly. How? First you converted the dynamic also into static. That you are measuring using the Pitot tube. Okay, the Pitot tube is this central thing which you are measuring. Okay, that is that is what is you are measuring here. That is the central thing. Okay, just not to confuse you. So I will do it once again. Look here, the pressure here is the stagnation pressure. What is its value? P2. Actually, what is its value? P1 plus half rho V1 square. So you go inside, same pressure is all air, let us say. Same pressure. So the pressure here is P2, which is actually P1 plus half rho V1 square. Whereas the fluid which is going by the side of this tube, there the pressure is P1. So if this is all air, the pressure is P1, and when you come here, the pressure is P1. Okay, but when you go down by height h, it is P1 plus rho GH, rho mercury into G into H, which is the pressure here, which should be pressure here also. Okay, so what am I getting ultimately? P1 plus rho mercury into G into H is P1, which is P2, but P2 is P1 plus half rho V1 square. So effectively, by measuring this height, you are measuring the dynamic pressure, and from there you can calculate V1. So this is the idea of a Pitot-Prandtl tube. So essentially a Pitot tube, basically what is it measuring? If you ask me, it is measuring the stagnation pressure. Pitot tube is measuring the stagnation pressure. So that means if you have a normal river, understand this, if you have a normal river and if it is flowing with the speed V1, so pressure at any point is P1 plus half rho V1 square. Normally if you try to directly measure pressure, you measure only this P1. But with Pitot tube, what you are doing, you are having this tube, okay, and by the time this water comes here, it stops. So the pressure here will become P2, which you are measuring, which actually is nothing but P1 plus half rho V1 square. This sum you are measuring. So you are able to measure both static plus dynamic by bringing everything to rest. Ultimately you are measuring it as static pressure only, but its value is the original static P1 plus the original dynamic now converted into static. Okay, so your Pitot tube is measuring the stagnation pressure, which is actually P1 plus half rho V1 square. That means, for example, if I am just giving an example, suppose if here the value of P1 is 2 atmosphere and half rho V1 square is 1 atmosphere. If you directly measure pressure here using some manometric technique, you will actually measure 2 atmospheres, which is the static pressure. But when the same fluid comes here and stops, you will actually measure the value here as 3 atmosphere, which is static only, but it is not this static. It is actually this static plus the dynamic which was there. So if you now take the difference, that comes out to be half rho V square. So Pitot tube is measuring the stagnation pressure, okay, which is more than the static pressure at other point in the moving fluid. Which is more than the static pressure at other point in the moving fluid. This is the idea. So this was something which I was missing in my lectures, and hope this becomes clear. So stagnation point is very important. So when you have an obstacle, Very near to the obstacle there will be a stagnation point where fluid comes to rest. Okay, where fluid comes to rest. If you use Bernoulli, because it came to rest, there the pressure will be quite huge, because the half rho v square term is getting 0 there. So the other part of this Bernoulli, the pressure becomes quite huge there. This is our idea. So this is something which was not there. I'll add it to our video series.